Crash Course Instrumentation, Diagnostics, Ep.5, Top Troubleshooting Techniques, How the Pros Track Down Faults. Welcome back to Crash Course Diagnostics. So far, we've talked about diagnostic mindset, logic, multiple faults, and how to stay grounded with first principles. Today, we're covering the real-world techniques techs use every day to find faults fast. From industrial plants to circuit benches, these are the most common and effective diagnostic moves. Split in half. Component swapping, signal tracing. Follow the fault. Let's break each one down with examples and historical context. Split in half, aka divide and conquer. If a system spans multiple devices or segments, test the midpoint. If the signal is good there, the problem is downstream. If the signal is bad, the problem is upstream. This technique is efficient because it cuts the search zone in half with every test. It works for voltage, signals, pressure, flow, logic errors, and software processes. Example: in a long conveyor belt system with multiple sensors and motor drives, checking signal continuity at the halfway control panel can instantly tell you whether to walk upstream or downstream with your meter. Historical spotlight. The divide and conquer method was formalized during WWII as radar techs used midpoint testing to diagnose large and complex electronic assemblies under pressure. Pro tip: start at the most accessible midpoint you can reach. Then test again to narrow the search zone. Component swap. Not every failure is obvious. Sometimes components fail subtly or intermittently. Swap it with a known good part. Same rating, same configuration. This method is effective for sensors, switches, relays, PLC modules, even power supplies. If the fault follows the part, you've found the issue. If not, look elsewhere. Caution: only swap after you've isolated the general fault area. Swapping too early can mask deeper problems or add new variables. Example: a technician suspects a proximity sensor is bad, but the input LED is still lit. They swap it with an identical spare and the problem resolves. Subtle degradation, like low voltage output, was the root cause. Signal trace. When you need to follow a path through a system, tracing the signal is key. Start at the source and trace forward step by step, or start at the symptom and trace backward. Use a multimeter, scope, or logic probe to verify signal integrity, presence, voltage, or digital state. This method is ideal for broken or miswired connections, terminal block errors, open loops in analog or digital systems. Pro example: in a bottling plant, a tech is tracking why the bottle count display stopped. Tracing the signal from the sensor to the PLC reveals a damaged terminal screw at an I/O card. Problem solved without replacing any parts. Pair it with schematics to save time and stay on track. Follow the fault. This is the reverse of a trace. You start at the symptom and work backward. Ask, what is supposed to happen here that isn't? Then work back one step at a time. What controls it? What powers it? What conditions does it need? This technique is powerful in layered systems, like automation lines or SCADA environments. Example: a tech is called to a boiler where the burner isn't firing. Starting at the ignition control module, they work backward and discover that a limit switch in the combustion fan line failed. No airflow, no burner. Sometimes, the obvious fault is just the last symptom in a longer chain. Wrap-up tip: use the right tool at the right time. Smart techs don't use one method for every job. They choose based on the system, the symptoms, and the context. A split in half is ideal when you don't know where the fault is. To swap it out is great for uncertain components. Trace the signal is critical when verifying connection paths. Follow the fault is powerful when symptoms are your only clue. Combine them, alternate, test smart. In the next episode, we'll talk about how to design systems for easier diagnostics, including smart labeling, test points, and operator clues. Like, share, and subscribe for more from Crash Course Diagnostics. Thanks to Tony Kuphaldt and the open source community at